Boosted and differentially private ensembles of decision trees, a joint work with Wilco Hennecke. There's an interesting observation in the world of decision tree induction, which is that if we don't care about privacy, then it is the boosting methodology which gives us the state of the art. Whereas if we do care about privacy, and differential privacy in particular, then it is random decision trees and random forests that currently reign supreme when it comes to prediction accuracy. The starting point of our work is the proof of a general privacy versus boosting dilemma when it comes to decision tree induction in the context of differential privacy. And we will also see how to operate on this dilemma with first the design of a loss with a particular knob, a knob making it possible to tune the stand against the dilemma, whether we favor more boosting rates or the spending of a privacy budget. And we will also see a way to operate this knob at runtime automatically with probable guarantees on privacy and boosting. So let's first review what are decision trees and supervised learning more generally. So supervised learning is the problem of learning functions mapping observations from a domain X to classes. We have two classes, -1 and 1. Alternatively, the models can output estimated probabilities for the probability that Y equals 1 given X, or eventually real values. A decision tree is just a particular way to implement these kind of functions with a very simple recursive partitioning of the domain at hand. The way we classify an observation is extremely simple and straightforward. We just traverse the tree from the root to a leaf, following the tests that are satisfied by the observation. The internal nodes of a decision tree implement tests on the description features until we reach a leaf. And the value of this leaf is then given to the observation, whether it is a class, a label, a probability, or a real prediction. Most algorithms implement a subset of three main steps. One is growing a tree from scratch. Another one is pruning a tree. A third type is the combination of various decision trees. And we can as well prune the ensemble of decision trees. In our approach, we have chosen not to consider pruning because first, it's costly from a differential privacy standpoint. It costs budget. And it turns out also not to be mandatory for boosting. And in this talk, I won't detail the combination part. I just focused on the growing part. And let's see what we mean by this privacy versus boosting dilemma. To start, we need to introduce what is the main component of classical machine learning algorithms, the loss function. In supervised learning, statistical decision theory gives us a simple but intentional peek on how to choose the loss, which is that bias prediction must be optimal for the loss at hand. It's called properness. When it comes to decision trees, we end up with a very general and appealing formulation for this kind of loss, which is just the expectation over the leaves of the tree of a function which is called the bias risk of the loss, computed over the estimated probabilities at the leaves. For example, if we pick the square loss, we end up with the Gini's criterion used in CART. If we pick the log loss, we end up with the binary entropy used in the information gain of C4.5. And if we pick Matsushita's loss, we end up with the splitting criterion of Kearns and Manso. We could as well pick the 0-1 loss, which has, by the way, a very simple expression. It would give the empirical risk, but this would arguably be a very bad choice for training. Let us now see what is boosting in the context of decision trees. So again, we have a very simple but efficient greedy approach, which is to start from a loss and equivalently from its bias risk. And starting from the tree reduced to a leaf, which is the root, we're going to recursively split the leaves of the tree to maximize the decrease in the expected bias risk at the leaves. And there's this key boosting result, which is very interesting for decision trees, which says that assuming the split we choose, gamma weakly separates the classes. It's called the weak learning assumption. It just means that in the two leaves that we get after the split, the classes are more separated than they are in the leaf that we have split. If we have this weak learning assumption, then we get guaranteed rates, and very interesting rates, depending on the bias risk, on the decrease of the expected bias risk. And because the empirical risk turns out to be upbounded by this loss, for many different choices and popular choices of bias risk, then we get a guarantee of decrease of the empirical risk as well. So let's now review a more general picture for boosting, assuming we get some sort of abstract scale in which we put the loss against its concavity. So somehow, as we move along this abstract scale, the bias risk of the loss, which is a concave function, it becomes more or less concave. Equivalently, we could index this axis by what is called the weight function of a loss, which is just negative the second derivative of the bias risk of the loss. Because it's concave, this function would be positive. So we have on the right-hand side just a few examples of what this could mean. How can we plot the boosting rates or represent the boosting rates against this abstract axis? Well, it's actually very simple. Because somehow the more concave is the bias risk of the loss, the faster is boosting. So boosting rates somehow go with a curvature. There's a whole set of results along these lines. And if we pick, for example, Matsushita's loss, then it actually achieves optimal boosting rates. It's different for the log loss, it's a bit worse for the square loss, and again, the 0,1 loss would arguably be, in fact, the worst choice of all. So let's now put differential privacy in this picture. So differential privacy consists in putting noise in the algorithm to ensure that the likelihood ratio of any outputs given two neighboring inputs is no more than a function exponential of epsilon. So we can bound this likelihood ratio where epsilon is the key parameter of differential privacy. It's positive, and as it decreases, privacy increases, but of course we put more noise, so the algorithm's utility, for example the accuracy in our case, decreases. A key property of differential privacy in our case is that it survives post-processing. There are two standard mechanisms of differential privacy used in decision tree induction that we have used as well, by the way. So the first one is the exponential mechanism, which randomizes a choice in a list of elements, a list which can be public. This could be the splits, the set of splits for attributes in a decision tree. If the splits are binary, then it's obvious that it is a public set. This is actually a very good choice regarding boosting, because the choice that we make may in fact not affect noise-free boosting results if the split that we pick meets the weak learning assumption. That's very important. And to label the leaves of the tree, we just use the Laplace mechanism, so it's a standard mechanism. We don't have any special trick, except maybe that we use the real value prediction mapped, using the probabilities mapped, using the loss canonical link. This is detailed in the paper. There's a key quantity for the exponential mechanism in differential privacy, which is that the sensitivity of the function used to rank outcomes gives us the amount of noise. This function is the maximal variation of the loss, in our case, on neighboring inputs, so neighboring datasets. The larger the sensitivity, somehow the more randomized is going to be the selection process. In Friedman and Schuster's paper, they give the analysis for three different proper losses, the square loss, so for CART, the log loss, so for C4.5, and the empirical risk as well. Our first problem was to essentially make this picture more general and end up with a general picture of sensitivity against the same abstract axis somehow of the concavity of the bias risk. And what we got is the following picture, which unfortunately says that sensitivity unfortunately goes with the curvature as well. So it means that the more concave somehow gets the bias risk, the faster is boosting, but the more expensive it's going to be from the privacy standpoint, the more noise we are going to put at fixed budget. There is therefore a clear dilemma emerging, which essentially tells us that we can eventually choose for fast boosting, but with the risk that we are going to put lots of noise in deciding splits, eventually destroying the purpose of boosting itself. Or we can stick to low sensitivity somehow, but then we'll have to boost longer to get accurate enough. And then at the end, of course, the budget being the total budget we will have spent, it could be big in fine. So how can we navigate this dilemma? Well, our solution in 2 steps starts from the design of a propulus with a particular knob whose tuning, in fact, is going to make us navigate the boosting versus sensitivity picture along the full spectrum. And second, a way to tune this loss or its parameter, this knob, at training time in a way that we are going to favor boosting over sensitivity near the root. So we are going to favor increasing the accuracy very rapidly, and we'll be happy to, let's say, have a larger sensitivity because we have more examples at the root used to split a leaf. It means also that we will have a good dependency for the privacy budget we're going to spend. And then, as we get down the tree and deeper in the tree, we are going to adaptively turn to favoring sensitivity and therefore the privacy budget over the boosting rates. The loss that we have created is a very simple construct from the partial losses of the 0-1 loss and Matsushita loss. So remember, the 0-1 loss is the worst for rates but the best for sensitivity. Matsushita's loss is exactly the opposite. So we end up with an analytical form for both the bias risk for decision tree induction, the sensitivity for differential privacy, and other functions as well, the inverse canonical link and the convex surrogate, which are very useful for boosting ensembles of decision trees. The details are in the paper. The summary of our theoretical results are as follows. We first give a complete boosting picture for the M alpha loss, so taking into account all ranges of values for alpha, which generalizes and turns out to improve as well the results of Kearns and Mansour. We have also a complete boosting pictures for the M alpha loss when we boost ensembles of classifiers, decision tree in our case. And also, finally, we introduce this way to tune alpha, what we call objective calibration, to ensure with high probability that all splits that we choose in a tree can actually comply with boosting. This goes with assumption, of course, the weak learning assumption being 1. So the details of this theorem and the explanations are in the paper. We have performed some experiments. We have compared our approach to state-of-the-art random forests with various tree size and ensemble size. We've considered 20 UCI domains from small to big, which means in our case in particular that we have induced more than 1 million models for various depths from 1 to 6, a various number of trees from 2 to 20 essentially, various values of the differential privacy parameter epsilon, 0.01, high privacy, up to 25, low privacy, various ways to fix alpha, so constant ways, so slow boosting but small sensitivity, fast boosting but high sensitivity, and also objective calibration. The results that we get give us a picture which is essentially domain dependent, but it tells us the following messages, as explained on and displayed on QSAR, for example. So here we are in a high privacy regime. What we get in this case is that objective calibration performs the best, and slow boosting, so alpha equals 0.1, is actually the worst. When we have a look at the average number of leaves, which is in the trees for a given test error, what we see is that we get with differential privacy essentially the same picture as without. So essentially to get smaller test errors, we need bigger trees. So without differential privacy, this is in total agreement with the boosting models. In domain UCI page, on the other hand, we have kind of an opposite picture, but notice in this case that epsilon is big, 25, so that's a small privacy regime. So in this case, using a slow boosting parameter, so alpha equals 0.1, gives us the best result. And somehow with with differential privacy, it turns out that the trees that are the most accurate are the trees with the fewest number of leaves, which somehow is the opposite picture of boosting without differential privacy. So that's interesting. If we conclude and summarize our findings, then we have somehow found a way to explain this sort of privacy versus boosting pictures in this state of the art. So better boosting implies higher privacy noise. Random decision trees somehow are cheap for privacy, but they are suboptimal, boosting wise. Achieving the best of both somehow may lie in a domain dependent, that's very important, sweet spots. Objective calibration can be a good candidate in the proper setting, and somehow it beats random trees and random decision forest, especially with small trees and ensembles. That's, we believe, are good news. And objective calibration does work on a wide range along privacy scale, which could eventually signal a very simple algorithm for non-private and private decision tree induction. Thank you very much.